Two lattices live inside four-dimensional space, and they look nothing alike. This chapter finds the exact matrix that turns one into the other, and the trap waiting on the other side. Two lattices sit inside four-dimensional space, the Hurwitz integers, H, the arithmetic engine of Chapter 1, and the D4 root lattice, the set of integer four tuples, A, B, C, D, whose coordinate sum is even. Their shortest vectors don't even agree. A Hurwitz unit has squared norm 1. A D4 root has squared norm 2. Different coordinates, different minimal norms. How could these possibly be the same structure? Split the integer points of H by coordinate sum parity. Even sum lands in D4 itself. Odd sum lands in the coset D4 plus 1,4,0,0 and stroke. The half-integer points split the same way, translated by omega, 1/2 times 1,1,1,1. D4 plus omega, and D4 plus omega plus 1,1 Four families, one lattice, H equals D4, together with three translated copies of it. Watch the shells sort themselves. N equals 1 and N equals 3 never touch D4 at all. They split evenly across the other three cosets. N equals 2 and N equals 4 land entirely inside D4. One transformation reaches across both lattices. M of I phi B, C, D equals A plus B, A minus B, C plus D, C minus D. It can't be an ordinary rotation. An orthogonal map never changes a vector's norm, and this one must. Instead, M transpose M equals 2I. So the squared norm of mx equals twice the squared norm of x, exactly. A Hurwitz unit of norm 1 lands precisely on a D4 root of norm 2. The mismatch between the two lattices was never a problem. It was the clue. Apply M to all 24 Hurwitz units, 8 integer, 16 half-integer, the vertices of the 24 cell. Every image lands on a D4 root, and every D4 root has exactly one Hurwitz preimage. M of H equals D4 is a bijection. The geometry hasn't changed. Same 24 cell, same edges. Only the coordinates and the scale are different. Arithmetic, geometry, and quaternion algebra, describing one object from two sides of a matrix. The 24 Hurwitz units are closed under quaternion multiplication. Multiply any two, and the result is a third unit. This group is the binary tetrahedral group, 2T. Now forget where the D4 roots came from. Take two of them, 1 TL by non 0, and 1 by norm 1 remark, and multiply their raw coordinates as quaternions directly. The product, 1,1,1,1,1, norm 4. Not norm 2. Not one of the 24 roots at all. Closure just broke. Did the group disappear, or is something else wrong? The group never lived in the coordinates. It lived in HM as a linear similarity, not a quaternion homomorphism. M of Q1 Q2 does not equal M of Q1 times M of Q2 in general. So transport the multiplication instead. Map back with M inverse, multiply an H where it's valid. Map forward again. X star Y equals M applied to M inverse of X times M inverse of Y. For our pair, M inverse of 1/20 is 1, M inverse of 1/1 of the mother is omega, and their Hurwitz product is omega. M of omega equals 1/1 back on the root lattice. Closure restored exactly. Not by accident, by construction. 3 layers, easy to conflate. The 24 cell, pure geometry. No coordinates at all. H and D4. 2 coordinate languages for that same geometry, related by M's quaternion multiplication. An algebraic structure that lives naturally in one language and must be carried deliberately into the other. The 24 roots, under the transported product, form a group isomorphic to the binary tetrahedral group, 2T. Build the norm doubling matrix. M, Classify each point by coordinate type and parity. 4 cosets. Verify M of H equals D4 is a bijection, not just a containment. Never multiply transformed coordinates directly. Transport the product. A lattice correspondence is not a multiplication correspondence.